So, I am going to talk about extracting gravitational wave signal from noise. And what is the problem here is that the gravitational waves are very weak, and even though the detectors have been made very sensitive, they are still deeply buried in the noise, and one must use mathematical techniques, statistical techniques in order to extract the signal from the noise. So, I am going to tell you all about that. So, first of all, let me say what are these gravitational waves, just remind you, because you already have had a few lectures on this. So, gravitational waves are ripples in the curvature of space time. As you know from general relativity, that was the theory given by Einstein, that gravitation is nothing but the manifestation of the curvature of space time. And since these are waves, gravitational waves, these are waves in the curvature of space time. They can be expressed in terms of the Riemann tensor or the metric perturbation that you have seen, and the waves, these are waves in the Riemann tensor r mu nu alpha beta, or the metric perturbation, which is h mu nu. You knew that you have written that g mu nu is eta mu nu plus h mu nu, and this h mu nu is a perturbation which is extremely small. Typically, it is of the order of 10 to the minus 20 something, minus 21, 22, 23, or even less. Normally, we will use the metric perturbation in the transverse traceless cage. This also you have done earlier, and it is written by h mu nu t t. And we will denote by h a typical component of h t t mu nu. And now, I will give you a sort of idea what is, how much is h, what is the order of magnitude of this h. First of all, the metric, as we have written, is dimensionless. So, there is no dimension in it. So, h is written also without any dimensions, and already I think these sources have been reviewed by earlier lectures. So, I will just give the values of h or the metric perturbation typically for different things, different sources. For example, the binary in spiral, if you take binaries of the order of the mass of the sun, whose masses are of the mass of the sun, then h is of the order of 10 to the minus 23 if the binary source is like 100 megaparsecs away from us. This is the typical distance at which such sources will occur. In fact, the first discovery which was there occurred something like few hundred megaparsecs away, 400 or 500 megaparsecs away. And the frequency is of the order of 100 hertz, because of our detectors are in the range from tens of hertz to kilohertz. So, we are typically giving these numbers for the typical kind of frequency bands and also distances and masses. For the periodic source, like a spinning neutron star, h can be even less, something like of the order of 10 to the minus 25, where this I here is the moment of inertia of the typical neutron star, and this is, it is about 10 kilometers in radius, and the mass is of the order of the mass of the sun. Then I is of the order of 10 to the 45 grams into centimeter square, and if its frequency is something like 500 hertz, that is the gravitational wave frequency, and it is within our galaxy, say near the center of our galaxy, then r would be like, the distance would be something like 10 kiloparsecs, and if it is an asymmetry of something like 10 to the minus 5, then h is of the order of 10 to the minus 25. While for the stochastic background, which can arise because of unresolved sources, this h can be even less, of the order of 10 to the minus 26. Now, given this, we must now look at the sensitivities of the detectors. So, what are the sensitivities of the detectors? So, here is the sort of progression of how the detectors have improved, and you can see from LIGO 1, which is the initial LIGO, to enhanced LIGO, to advanced LIGO, and so on. And the bottommost curve, basically you see in purple, is the LIGO, is the curve for advanced LIGO. And what is plotted here is the square root of the power spectral density versus the frequency. Now, what is the square root of the power spectral density? I will come to. I will explain all this in my notes when I write down properly the notes and all that. I will say that. But this is basically the level of noise with which the signal has to compete. And signal, as you saw, was 10 to the minus 23, 10 to the minus 25. Therefore, the signal is buried inside the noise. So, now I will go to the thing about the extracting the signals from noise. So, signals are buried deep inside the noise. So, signal processing is necessary for detecting, estimating the parameters of the signal. So, even for detecting, you have to say you have to actually do operations on the data, which is called filtering, and this is what the rearrangement of the data, as we say, and performing algebraic operations for data can reveal the signal. So, it is basically you are combining the data in certain ways in which the data shows you that there is a signal. So, that is called filtering the data. So, this is very necessary in the case of gravitational wave signals, because they are weak first of all, and they lie inside the noise in spite of the fact that the detectors are so sensitive. So, now I will show you an example of a filter. We have a signal which is, say, sinusoidal. It is just a perfect sine wave or a cosine wave. Okay. So, the data now is the signal plus the noise. So, when you add the noise to the signal like this, it is called additive noise, and we assume additive noise here because our signals are so weak. So, suppose our data is signal added to the noise, and then you can't see anything here. So, your signal is St, which is A naught is the constant, cos 2 pi f naught t. So, that is f naught is the frequency of the signal, A naught is the amplitude of the signal, and this St, the signal, is embedded in the noise. You can't see anything. You can't say that there is a signal in this noise. You can see the picture which is there, the diagram is there, and f naught is in fact 256 hertz, which I have written down here. Now, what is the filter for this? The best filter for this is in fact the Fourier transform. If you take Fourier transform this data, immediately the signal stands out. How? You can see it here. Best filter is the Fourier transform, and if I write x tilde of f, that is the Fourier transform of x of t into e to the 2 pi I f t dt, you integrate over the time from minus infinity to plus infinity. Ideally, of course, you do not have infinite data, you have some finite data, but we take this ideally, that is minus infinity to plus infinity. You calculate the Fourier transform, and the statistic, as it called, that is the measure of what you will compare with the rest of the data, that is the statistic, that is C of f. It is mod of x tilde of f. Okay. So, if you look at this and you plot this C of f versus f, then you can see that there are two big peaks here. These peaks are at minus 256 hertz and one at plus 256 hertz. And these peaks tell you that there was a signal, and because this was just a Fourier transform, it tells you that your signal was actually a sine wave. It was a monochromatic wave of frequency 256. So, your statistics not only tells you, if you put a threshold here, for example, just below the peaks, then you can say that you have detected a signal of a certain frequency, which is 256 hertz. So, the match, this is in fact a generalization of this is the match filter. This is an example of a match filter for a simple signal. So, what I am going to now talk about in this particular talk is, I am going to talk about the match filter. So, what is the match filter for the binary waveform and so on? It is because of the fact that it is only binary sources or compact binary events that have been detected so far. Most of them have been black holes and one neutron star binary. So, it makes sense for me to talk about how to do detection of a binary system. So, I will talk about match filtering and how to use the match filter in order to pull out the signal from the noise. So, that is the basic thing in this lectures which I am going to carry out. So, now just to give the statistical problem. So, what is detection? A detection is a statistical problem. The data consists of signal plus noise, and the detection of the signal is always a decision which is based on probabilities. One can never be sure, 100% sure, that there is a detection. That is for anything. So, even when you say that something is there, okay, there is an object which is over there, you might say that, oh, 100% we have detected that object is there. It is not like that. That object may not be there, and you are making a statement of a very high probability. It may be that that object is there with a probability of 99.99999%, some one part in 10 to the 7 or 10 to the 8, it is not there. But there is, the probability is never 1 of detection. This is the point which I want to make. So, here also when we say, when we make a match filtering or when we do this analysis for our signals and we say that a detection is announced, it is always with a certain probability. So, the goal of detection theory is this, that you assess the probability of detection, provide confidence limits, and often one must search within a family of signals. For example, I mean, if you take the compact binary systems for example, then there are masses. You can have these binary systems of any masses. They can range from a solar mass binary systems to maybe 50 solar mass binary systems or 100 solar mass binary systems. One may be 5 solar masses, another may be 30 solar masses. As it happened in our first detection which we saw in the discovery, there were 29, one particular black hole was of 29 solar masses, another black hole was of 36 solar masses. So, all these different, if you change the masses, the waveforms change. So, you have to search your signal in the data among a family of signals. So, one must, so anyway one has to in fact decide on what is the signal before actually proceeding with the analysis. So, this is what I want to say here. Now, I will go to do some preliminaries about detection theory and so on. What is a data segment and things like that. So, the data that comes from the detector is time series data. So, we represent it by a letter x. Okay. So, we write it as x of t. Okay. So, that is your data. And we consider data segments. Data segments in the time range 0 to t say. So, this is an interval, a time interval 0 to t. Okay. And we sample this because anyway we are doing all this analysis on the computer, we can only do it with finite number of samples. So, we sample this data. So, sampling of 0 t is the following: sampling of the data segment. Zero t, and I will draw it as a line 0 to t, and I sample it like this. And I will take n samples, capital N number of samples. So, the first sample is I will call t 0 and the next t 1 and so on. Finally, here there is some t k, and this sample which is 1 before t is t n minus 1. Okay. So, that is the sample here. The next sample x of x at capital T in fact belongs to the next data segment, that will be t 0 of the next data segment. So, we do not take that into account, and the samples are denoted then by the letter x. So, it is x t naught, x t 1 and so on, x t 1, x t k and so on up to x t n minus 1. So, these are our samples of the data. Okay. And generally, unless called for some special cases, what we do is uniform sampling. So, uniform sampling, that means the time interval between each sample, the two adjacent samples is a constant. So, x t k or x k we write as x t k, so which is x of k delta, where we have taken, where this delta is t divided by n. So, t delta is called the sampling interval. Sampling interval. So, this is how it goes, and so you take the sample at t k. So, t k is k times delta, and k goes from 0, 1 up to n minus 1. So, this is what it is there. So, you have a whole set of samples xk, n samples which go from 0 to n minus 1. So, one can in fact, it is convenient in fact to think of this xk, all these xk's as components of a vector. So, you think of xk as samples either of all these things as a vector, and which I will write here x bar, bar means a vector, x 0, x 1 and so on up to x n minus 1. So, x bar is an n dimensional vector and x's are the samples which in our case are real, but if you take Fourier transforms and all that. So, then in that case we will allow the each particular component to be complex. So, we will in general talk of Cn or Rn, instead of Rn we will talk of Cn. So, this is the thing, and the space of all data trains. So, you will be all sorts of possible realizations are possible for the data. So, the space which is there, the space of all data trains, we will denote by this script d. So, script d means the space of all data trains, and here we have x bar belongs to d. So, we say that x bar is belonging to d in this thing. Now, what is this x bar? X bar is in fact a random vector. Okay? So, because there is noise in the detector and the data is noisy. So, now the x bar in fact is a random variable, and so we have to do some statistics. Is a random variable because the data contains noise. Contains noise. Okay. And right, and so because it is a random variable, it has a certain probability distribution. So, we have two kinds of things which we consider. If the data is just noise, if the data contains just noise, that is x bar is we will write as n bar, n is noise, n stands for the n letter stands for noise, x bar is n bar, or it might contain a signal. Data contains noise plus a signal here. In that case, x bar is n plus some signal which will denote by h, another vector h bar. Okay. So, in this case we are thinking of one signal, it could be any type of signal, the h can depend on many parameters and so on, but we will come to that later. And because this is a random variable and we are talking of statistics, there are probability distributions associated with this. So, here in the first case it is customary to denote the probability distribution with the noise by p naught of x. P 0 of x means this is the probability density of the data when it contains only noise, no signal. And here we have, as you have seen here, as I see here, x bar is n plus h, we have considered additive noise, and that is justifiable because our signals are extremely weak and we can think of the signal just adding to the noise. In that case, we denote this particular probability distribution by p 1 of x bar. Okay. So, this is a customary thing in statistics. Okay. Okay. So, now let us talk of the statistical. Since this is a random variable, we can think of statistical properties of the noise. So, there are many things we have to learn about. One thing is I had plotted that square root of SH of f and so on. What is SH of f? That power spectral density of the noise and so on. So, that is the thing which I want to define, and also other things like significance of a detection and so on. So, statistical properties of the noise. Of the noise. So, one thing which I want to talk of is the color of the noise and so on. So, first of all we assume that the mean of the noise, that the average of the noise at any time t is 0. So, what is this n of t? Just as x of t was defined on the interval 0 to t, n of t is also a function of t. It is a random variable on at every time t. So, for each fixed t, if you take n of t, you take the mean of this is 0 or the average value of this. Now, what does this angular brackets mean? So, this is called 0 mean noise. Let me write that 0 mean noise. So, what do these brackets mean or the angular brackets mean? The ensemble average. Yeah, ensemble average. So, over what are called identical detectors. So, what you are doing is you are considering whole lot of detectors, an ensemble of detectors, large number of detectors which are identical. And now you look at the n of t in each of these detectors, take the same time t and take an average at that time t of all the different samples in the different data streams that you get from the detectors. So, in other words, you have got a whole lot of detectors here 1, 2, 3 like this, your data streams. So, detector 1, detector 2, detector 3, this is 0, this is t, and here you mark out 1 t in this is time t, okay, and you pick up the noise sample here, noise sample here, noise sample here, and take an average and let the number of detectors, such identical detectors, go to infinity, and then take that average, and that is in fact the average ensemble average of n of t, and that we assume to be 0, which means that we have actually subtracted out the DC component. So, even if it is not 0, we can always subtract out this DC component of the noise and make the noise, the mean of the noise to be 0. So, now next thing we define is autocorrelation of the noise. So, autocorrelation of the noise. So, what is this? This is defined as the ensemble average of the product of n and t prime. Okay. So, this is like a covariance, this is just a covariance here, and which we denote by a function which is k of t prime. Okay. It is clearly symmetric and so on, and this is called the autocorrelation function. And we now further assume that our noise is stationary. Then in that case, this is in fact a function of t prime minus t or t minus t prime. Okay. So, the noise is stationary. If you make assumptions only on these first two moments, so now we have talked the first moment is the mean, the second moment is the covariance. So, if you only make assumptions about this and say this is called wide sense stationary, which is more general than stationary noise, where you assume stationarity over all other moments also. So, this is generally denoted by wide sense stationary, or in short this is called WSS, okay, wide sense stationary. So, if you write now tau equal to t prime minus t, then the same equation can be written as n of t plus tau is k of tau, where k is called the autocorrelation function. So, k of tau is called the autocorrelation function. Of the noise. In general, it looks something, it's like a something like a bell-shaped function. So, it looks something like this. If I plot this k, it looks something like this. So, this is k and this is tau. So, it looks something, it is symmetric of course, and it looks something of this sort. So, now when you take you can actually now go to the Fourier domain and look at this, how this looks like. Okay. Since there is this, what this wide sense stationary or stationarity means, that the noise, autocovariance, covariance and all that, these properties don't depend on absolute time. That is what it means when you take only the difference is what matters, t minus t prime or t prime minus t. This is what the whole thing says here. And n t equal to 0 means it is anyway stationary, it is not changing, the mean is not changing. Now, going to the Fourier domain, we write n of f as the integral of n of t into e to the minus 2 pi I f t dt. Okay. So, we take this integral, and in this case, since we have taken only 0 to t, the integral will be just 0 over 0 to t, but anyway I will not write that down. So, if you now take the average value of n of f and n star of f prime, because now n of f, n tilde of f is complex. As you can see, here is a complex factor has come in, e to the minus 2 pi I f t. The n of f is complex number. So, this is a complex number here. So, now n of f, n star of f prime is in fact s of f delta f minus f prime. You can show this if you have a noise which is stationary. So, you can prove this by using all sorts of Fourier transforms, the inverse Fourier transforms and delta functions, and all that will tell you that you can do this kind of thing here. So, what I would like to say is that we have, earlier I had talked about the data as samples and so on, that is good for computing and things like that. But when we are discussing the statistical properties, I will be continuously switching from the discrete domain to the continuous domain. So, it does not mean anything very much that the samples are so close, I mean in terms intuitively you can think of this as a continuous thing. So, whenever it is convenient to write integrals, I will write integrals in this thing. In general, all these integrals and so on can be converted to sums and so on when you are talking of samples and discretizing things. So, when you are in the discrete domain, you simply take discrete samples there. So, this is S of f. So, this is S of f, in fact is called the PSD of the noise. Now, since we will be talking of the basically the signal channel is denoted by h of t. There is a h which is added, just put as a subscript of f. So, I will put this h here, because our data which we will be taking, the time series data, will be the data from the signal channel of the detector, and that channel is denoted by h of t channel. So, I will put a subscript h for this S of f. So, sh of f is in fact called the power spectral density, PSD, okay, in short, of the noise. Remember that this sh of f had occurred in one of my plots which I showed there when I showed the noise curves. So, the noise curve showed square root of sh of f versus f, okay, for advanced LIGO, initial LIGO and so on. So, first thing we have defined here is this sh of f, and if sh of f is a constant. So, just to tell you that these are terms which are used here, the sh of f is a constant, then it is called white noise. This is called white noise. This is an idealization. No, noise is never white, because anyway any detector or something has a bandwidth. So, the noise is going to be changing at least outside the bandwidth. but approximately if it is flat, this curve SH of f is roughly flat, then you can think of this SH of f as white noise, at least in that band. Okay. So, that is why this white noise thing sometimes is convenient fiction to use when we do some calculations. If the noise SH of f is not a constant, then that is called colored noise. SH of f not a constant, then it is called colored noise. So, these are some of the terminology which enters into this thing. And one other thing which I would like to mention is the dimensions of this quantity. Now, you can go back and see here that n of t and so x of t, the h which was there, the h mu nu which is there is dimensionless, as I said before. So, the data stream which is there is dimensionless, there are no dimensions to this. But when you take n of f, the Fourier transform, there is a time coming into it, there is a time there, and because the time comes into it, n of f has dimensions of time or Hertz inverse. So, now when you look at this equation here, the angular bracket of n of f times n star of f prime equal to sh of f into delta f minus f prime, the left hand side has dimensions of t square of or Hertz to the minus 2, delta f minus f prime has dimensions of Hertz inverse. So, SHF has dimensions of Hertz inverse. So, dimensions of this is Hertz inverse if you are measuring your time in seconds. So, this is what I wanted to say about the color of the noise. Now, there is another property of the noise which is the probability distribution. So, the whole random vector x of t has a probability distribution, and that probability distribution can be anything. So, one of the most important things which is there, that one of the most important distributions which comes about because of the central limit theorem and all that, is that the noise is usually Gaussian in many of the detectors which are well understood. So, what is Gaussian noise? So, anyway, this is a idealization in this case for our LIGO detectors. So, anyway, we will do this case of Gaussian noise. Okay. So, what is Gaussian noise? Okay. So, we take the autocorrelation function which is there and define a matrix CIK, which is k of TITK, k of TITK, which is NIK. Now, look here. So, now we have taken those continuous domains so far, but sometimes it is now good to go to the discrete domain in order to define these things like Gaussian noise and so on, the probability distributions. Okay. So, CIK is KITK, which is nothing but NINK, the ensemble average. So, multiply the ith sample by the kth sample, take the ensemble average over identical detectors, and what you get is this CIK, which is basically the covariance matrix. Then the probability distribution, which is Gaussian, is given by P of x bar is 1 over 2 pi raised to n by 2 square root of determinant of C and e to the minus half x bar transpose, I will explain all this, C inverse x bar. And so, what this means is that you take your random vector which is x bar, which is the x 1 up to x t n or x n minus 1, and you think of this as a row vector. Now, if you write this with a transpose, it becomes the column vector. Take the column vector x bar t, multiply by the inverse of the matrix C, CIK we have defined earlier. This is the matrix C. So, this is the matrix C. Take its inverse, then again multiply by the vector x, you get a scalar, and this is the quantity you put in the exponent of e raised to that. So, this is in fact the thing here which tells you that you have got a Gaussian distribution. So, in 2 dimensions, for example, this thing may look something like this. If I plot it, this is P x naught x 1, I just take 2 samples, then this may look something like this. This whole thing looks something like this. This is the kind of a Gaussian distribution. And the outside factor, the amplitude outside, which I have written down here, 1 by 2 pi raised to n by 2 and square root of determinant of c and all that, is the normalization factor, which makes the integral of px dx. So, px dnx, it is an n dimensional vector, is 1. So, the probability is all added up to 1 as it should, okay, in this thing. So, we could write in fact px as this quantity into px can be also written as a n, some amplitude or the constant factor into e to the minus half x bar t c inverse x bar. Okay. So, this is the kind of thing, and we can write this as a n and write it in terms of e to the minus half. C inverse can be written as a matrix which is the inverse of the matrix, say mu I k. Okay, we call this matrix mu I k. Then this is half mu I k x I x k. So, this is writing it down in terms of the components of the vector, and now I have raised the indices of these vectors, and I also use the Einstein summation convention, where the I and k range from 0 to n minus 1. So, this is a double sum, in fact involving several terms. It is something like n square, order of n square terms over there, and this can in fact further be written down as e to the minus f mu I k minus half x bar with the vertical line x bar, like a scalar product. So, we can, so this motivates in fact a definition of a scalar product. So, the scalar product is this scalar product. This scalar product is defined on D. D is your space, space is a vector space, and this becomes in fact what is called the inner product space, but we may not get into that. X bar, y bar, we define the inner product as mu I k x I x k, x I y k. Okay. So, that is your scalar product over here. And in the continuous domain, in fact this goes to minus infinity to infinity x tilde of f star y tilde of f, this is the Fourier domain, sh of f df. So, in the continuous domain, in the Fourier domain, this goes to this, and if you go to make a continuous transformation to the continuous domain, it is just this kind of scalar product plus a complex conjugate, which will come here to make it real. So, this can be written many times. This sh of f is, because it is a real thing and so on, this sh of f can be turned on itself. That means, sh of minus f is sh of f and so on. Then it is called the one sided PSD, and often it is written as this whole scalar product written as 4 times the real part of 0 to infinity x star of f y of f sh of f df. So, remember this kind of a scalar product which often occurs in gravitational wave data analysis. So, what has come down is it is weighted. So, it is basically like our usual Euclidean scalar product x dot y, x 1 y 1 plus x 2 y 2 plus x 3 y 3 and so on, but it is weighted by the factor 1 over the inverse of the power spectral density. Okay. So, wherever, so what this means is that the scalar product is weighted by those those components of the vectors are important where the noise is less. Where the noise is less, the sh of f is smaller, and those components are enhanced by this particular scalar product. We can now go over to the so called detection problem. So, what is the detection problem? So, we have to say whether we have detected a signal or not. Okay. Given a data vector or data train, we have to say whether there is a signal lying in it or there is no signal lying in it. So, this is called the detection problem. So, I write down here detection problem. Given x bar, decide whether a signal is present or absent in the data segment, in fact, which you are taking in the data segment. So, first let us consider the case of a known signal, just one signal which is known and only one, okay, as opposed to having a family of signals, only one, and we will denote that signal by h bar. The h bar is the vector which is there. So, now this is called hypothesis testing. H naught is the hypothesis that signal is absent. Signal is absent from the data. So, then in that case x bar is just n bar, and the probability distribution which we had assigned to this is P naught of x bar. And then there is the hypothesis H 1 when there is signal is present in the data. Then in that case x bar is n plus h bar, okay, and then the probability distribution is P 1 of x bar, okay. So, that is the notation. And for additive noise, if you have the noise to be additive as we have taken here, P 1 of x bar is nothing but P naught of x bar minus the signal, okay. It is the same thing as the noise. You subtract out the signal, you get the probability distribution of the noise. Now, we have to say, given x bar, what is the, whether there is a signal in that or not. So, what does a test? So, we have to design a particular test. So, this is called a test. So, test is what? Amounts to actually partitioning D, amounts to partitioning. Partitioning a set means you break it up into two parts such as the union is the set and the intersection is empty. So, partitioning D. So, D is written as some region R plus R complement. So, C on the top denotes complement. So, D is R union R complement, okay, and of course, the intersection will be phi. If x bar belongs to R, then the signal is present. Is present, and if x bar belongs to R C or R complement, the signal is absent. So, what does it mean? This particular problem of detection amounts to partitioning D into two particular regions, and if you get a particular vector x bar, then you have to see whether the x bar lies in R or whether it lies in R C. So, your detection problem actually amounts to partitioning D into R and R C. So, what is R? What is R C? That is the problem. So, pictorially if I draw, I can think of this as a space of data trains like this, and this is the origin where the noise may lie. So, this is R C and this is R, and if your data vector lies here, you will say that the signal is present. If it lies within R C, you will say that the signal is not present. So, the whole problem now lies in finding R, and for this there is a very nice criterion which was given by Neyman and Pearson, okay. So, Neyman-Pearson criterion is the criterion which is used. So, Neyman-Pearson criterion, for this I have to define two things. One is what is called the false alarm, PF of R, probability PF of R, which is the integral over R of P naught x bar dnx, okay. This is called the false alarm probability. This is the probability of saying there is a signal when there is no signal, in fact. So, that is a false thing that you get a trigger, say in your you think it is a signal, but it is really not a signal, it is just noise masquerading as a signal. So, what is this probability? That is called the false alarm, okay. So, saying there is a signal, there is signal when there isn't actually, when in fact there isn't. The other probability of importance is the detection probability. It is also over R, and but it is the integral of P1 x bar, dn x bar. So, it is an n dimensional integral over R. So, this is saying there is a signal when it is actually there. Okay. This is called the detection probability. And what is the Neyman-Pearson criterion? It is maximize the detection probability, maximize PD for a given PF. That is, if you fix your PF to be something, maybe a very small number like alpha, then you maximize PD for this thing, for this particular false alarm probability. So, you have to find a region R which basically does this. And this is the right kind of thing for our sources like binaries and so on, when your signals are rare and you do not know what costs that one can assign and so on, and there is a whole description, and that is, the description is already given in many books, standard textbooks like C.W. Hellstrom and so on. So, this is the criterion, and there is a Neyman-Pearson's lemma. There is a theorem which tells you how to find this region R. It gives you a prescription. So, what is the prescription? Prescription is define a likelihood ratio, define a certain quantity which is called the likelihood ratio, define the likelihood ratio lambda x bar equal to P1 x bar over P naught x bar. Then just lambda x bar greater than some constant lambda naught, which is in fact called the threshold, defines R, defines the region R where lambda naught is fixed by requiring PF equal to alpha. Okay. So, by requiring just this thing, and lambda naught is in fact called the threshold, In fact, this surface which I have drawn here, this curve which I have drawn here, depicted here, is lambda x equal to lambda naught in fact over here. So, this is what it tells you. So, immediately it solves the problem for you, that this is the detection problem which is solved in this way. So, let us do this for Gaussian noise. So, suppose your noise is Gaussian, then you, for Gaussian noise, there is some calculation one has to do. The likelihood ratio in fact can be replaced by just the correlation or the scalar product which is just equal to C of x bar equal to x h. It can be replaced by just this. This works just as good because lambda x is a monotonic function of C x. So, you can use any monotonic function of the likelihood ratio to decide whether the signal is present, and put a threshold on C. So, which may be eta or whatever you want to put on this thing. Now, C of x h is what? You can write this down is mu I k x I h k, okay, in this thing. So, which is you can write down is as q I x I, where this q I is mu I k h k. Okay. This mu I k is in fact called the match filter, and this is in the continuous domain. If you go to the Fourier, this is just S h of f over f. Now, you can see how all these things are coming up, that you had the Neyman-Pearson lemma. It told you how to divide your space of data trains into those regions R and R complement, in which you can say that there is a signal present if x bar belongs to region R, otherwise it is absent. Okay. And that region is fixed by requiring that the detection probability is maximized for a given false alarm. That is guaranteed by the lemma. Okay. That is called the Neyman-Pearson lemma. And what this has told you is that if you take Gaussian noise, the lambda x is basically the correlation C of x bar, which is the scalar product of x bar with h, which can be written as mu I k times xi times h k, and where this q I is x I. So, you can write the mu I k h k as q I x I, and q I is mu I k h k, and which in the Fourier domain or in the continuous domain simply goes to this, and this is called in fact the match filter. So, this you write as q of f. You can put any constant outside, it does not depend on the constant. You can always normalize this particular filter. You can usually normalize it so that the filter scalar product of the filter with itself is 1. So, you can put a normalization and it does not really matter to this thing. I mean, you can multiply that, that is also a monadic function. So, lambda x is also monadic function of this particular function over here. So, this q of f is called the match filter. Match filter, and what this tells you is that the match filter is optimal for signal extraction in Gaussian noise in the sense of Nabbe and Pearson. That means, given a false alarm probability, you can the detection probability is automatically maximized for such a filter. So, that is a big advantage, but unfortunately, we are not in this situation. This is for single signal which was there, only one signal which was there. But we have a family of signals, because as I said, we do not know what will be the masses of the stars, we do not know the spins of the stars, we do not know what time the signal will arrive, we do not know what is the phase of the signal. These are all unknown parameters, and so we need to search over this family of signals. So, we have in fact a family of signals which depends on many parameters, depends on parameters like the amplitude, for example, phases, masses and things like that of the binaries. So, in general we can call these parameters lambda alpha, okay. We call them lambda alpha, where alpha goes from 1 to up to m, say. So, this is up to m. So, m dimensional space basically you have here. So, then the strategy just changes different. I am not going to go into the full details, but if you have a strong signal, as we will have here, like signal to noise ratio of 8 or 10 or something like that, the lambda you maximize this lambda max x you define as your statistics, you maximize these things, you have lambda x bar lambda alpha. So, what happens is that when you have a family of signals, the P 1 x which was there earlier, the P 1 x becomes P 1 x semicolon lambda alpha. So, what happens is that the P 1 which we had here, P 1 x, for the family goes to P 1 x bar lambda alpha, and then you can define lambda bar this alpha as P 1 x bar lambda alpha over P naught of x. Now, if you maximize over lambda alpha belonging to some space or some subset u of the m dimensional space and take the maximum, then this works as the statistics, and then what you will demand is that you decide on detection if lambda max now x is greater than some threshold lambda naught, which is again decided by the false alarm. This is called maximum likelihood detection. MLD in short, this is called MLD.